Hiya! New chapter, linear programming, one of my favourites, as always. A lot of this you will recognise from GCSE. So inequalities, plotting them on a graph, shading a region. The only difference really is this time we have to formulate the inequalities and then we'll be able to find a region of the graph where some of the solutions are. And we'll meet techniques later that allow us to find the optimum solution. So there's some new terminology here. Decision variables, objective functions, constraints. What I thought we would do is look through an example together. So you've got 3 examples in your textbook. I thought we'd look at question 2 together, which is on page 143. And we'll talk through decision variables, objective functions and constraints. And then in the up and coming lessons, we'll look at plotting these, how to find the optimum solution, what happens if we want integers, that kind of thing. So, question 2 on page 143, we have a situation where a floor display is needed for a new building, and there are certain constraints which are to be put in place. Now, the decision variables are really important to set up, and if you don't do them right, you will lose marks. So it states in the question what they want x and y to be. So x is going to be, let x equal, x is a number of type A plant. It's very important that we put number of type A plant. It is not type A plant, it's the number of. And Y is the number of type B plant. Lovely. So they're my decision variables. And that is what's going to make up my formulation. The objective function is the aim of what I'm trying to do. Quite often I will want to maximise profit. Sometimes I want to minimise cost, and in this question they want to minimise the cost of the floral display. So we are going to minimise, I'm going to use C to stand for cost, and to minimise the cost I need to look at how much each of the plants costs. So type A costs £6 and type B costs £10. So if X and Y represent the number of type A and B plants at a cost of £6 and £10, that would give me my overall cost. Now, obviously, I want certain constraints in place because otherwise this could be anything. It could be any solution. But some of the constraints I've got in place here are very clear in the question. Others are a little bit more vague and take a bit more working out. The first one that's quite obvious is the length. Now I've put here subject to. I will often use just ST to stand for subject to. Now I'm going to have a constraint about length because it tells me that type A plant is 1 metre in length, type B plant is 1.5 metres in length, and we've specified that the display has got to be at least 30 metres in length. So 1x plus 1.5y has to be at least 30 metres. So that's one of the constraints that we've been given. I would go through and times all of this by 2 just for when I wanted to plot it. So that's the original constraint, but this second one here would be a lot easier to plot on a graph. There's one constraint done. If I look through the question, it talks about at least 6 of type B plant being needed. So Y has to be at least 6. There's our second constraint, and that's to do with the number of type B plants. There's quite a challenging one about wanting at least twice as many as type A and type B plant. And I often get this the wrong way round. So, have a real think about it. I sometimes like to put numbers in as well to make it a little bit easier. So x is greater than or equal to 2y. So this is, we want twice as many A as we do B. So that's my x and that's my x and that's my y. I sometimes put numbers in, like I said, to help me out a little bit. So if I put a 3 in there, 2 times 3 is obviously 6. And in this case, you can see that I now have got twice as many y, twice as many x as y. Okay, so the 2 has to go here to make that double. Okay, I hope that makes sense. Like I said, it always confuses me and I always have to put numbers in to try and help. So I've got my next constraint there as well. Now I've got this thing at the bottom called non-negativity. And that's needed just to ensure that I don't get any negative solutions, because quite often in a question like this it wouldn't make sense to have a negative number of type A plant and negative number of type B plant. So we specify this non-negativity constraint at the end. We don't often have to plot it because we only look at one quadrant anyway. So we've got our decision variables, objective function, and these are the constraints that limit our solutions. So if I was to plot these, so 1, 2, 3, I would plot those onto a graph and it would give me a region that would have several solutions within it. Later on in the chapter we'll look at ways to figure out which of those solutions is the optimum one. I hope that's helped a little bit. Have a go at the questions in the chapter that I've specified on the Show My Homework instructions, please. Bye for now.